Welcome back, Calculus 2 students. In this lesson, we are going to discuss how to find the length of a curve that is described by parametric equations. So let's suppose that we are given a curve. I'm going to draw that in red. That has specified endpoints. Maybe we'll say x is x of t, so some function of t, y is y of t, so that's going to govern the nature of the behavior of the curve. But we're going to say that t is between, let's say, alpha and beta. And so this point we'll, for example, assume is when t is equal to alpha. Over here, t is equal to beta. And we'd like to know the length of that segment of the curve. Our strategy is going to be, as it is in most calculus topics, to subdivide the problem into a finite number of easier problems where we approximate, and then take the limit as those number of subdivisions goes off to infinity. So let's break our curve into some pieces here. And what we're going to do is replace or approximate each little segment of curve by a line segment. And so you have the red curve, and then we have all these blue line segments. These are all straight segments. And I'm going to label the lengths of these segments as follows. So that length is going to be delta S1. Now I have delta S2, delta S3, 4, and so on. And so in this particular drawing, I've got delta S1 to delta S8. Remember, delta is often used to represent a change in something, a change in a variable. And so right now, I'm regarding the length here as S. And so I've got all these small changes in S on the smaller intervals. We'll see a little bit more about that later. When I start relating this to the x and y, it'll make a bit more sense. And then let's do that now. So let's zoom in on one of these segments of the curve. And suppose it's got these two endpoints, and then some line segment that's joining it of length delta Si. So we're going to use the Pythagorean theorem to calculate the length of that in terms of the change in x and the change in y. So down here, we have the corresponding change in x. Over here, we have the corresponding change in y. Now I've labeled these delta xi and delta yi. I think for the most part, the consistency in notation is going to make this easy to understand. But you may be perplexed why I'm not just using delta x, as we often do when we assume a regular partition. And the major reason is that x and y are both functions of t. And so at its core, I'm really thinking of partitioning the t values between alpha and beta. And that, no matter how I partition it, may result in an uneven and irregular partition of the x's, as it often does with the y's. And so this is really a difference of x values, this is a difference of y values, and that may change on each little interval. So we're going to use delta xi and delta yi to keep it simple and consistent with the notation we have there. All right, well, by Pythagorean theorem, we know that we have delta Si squared equal to delta xi squared plus delta yi squared. And if I want to work t into this somehow, one good way is to, on the right-hand side, I'm going to divide by delta t squared. And I'll do that in this manner. So the delta xi squared is getting divided by delta t squared. And so now I'm going to assume a regular partition of our t values from alpha to beta. So I add a little bit to alpha, then a little bit more, then a little bit more, and eventually I'm going to get caught up to beta. The length of each little t interval is delta t. Over here, I'll do the same thing, dividing by delta t squared. Now, if I left that alone, that would be a huge mistake. I can't just modify the expression, but I can compensate for it right here. So if you were to redistribute delta t squared into the brackets, it would cancel with these denominators, getting you back to that previous step. I can solve for delta SI with a square root. And there are some assumptions that I'm glossing over here in terms of the full general version of this could allow delta t to take on negative values, and I'm not really worried about that level of specificity here. But I'm going to take the square root on the brackets, and then of course the delta t squared, I'm going to change to delta t, again glossing over some of the inconvenient possibilities that could happen. All right, so that's going to be the delta SI. That gives an expression for each of these guys in terms of x and y and t. Why do we care? Well, if we're trying to get the length of this curve and we're going to approximate it by adding up those lengths there, delta S1 through delta S8, then we can represent that with a sigma notation, where I is going from 1 to whatever n we stop with, and then we can let n go to infinity, as we often do with Riemann sums and other summations that are tied to integrals. So now we can actually substitute in place of delta SI that monstrous expression over there. So we'll have a big ugly square root times delta t, and inside that big ugly square root is going to be a couple of squares, namely delta xi over delta t and delta yi over delta t. Now again, without doing the rigorous proof, we expect this limit of a sum to somehow connect to an integral. And in fact, it's going to be the integral involving t values, alpha and beta, as the limits of integration. And then we'll have a square root dt. And what goes in the square root? Well, the delta xi over delta t, that is exactly the expression we associate with x prime of t. And the same thing for the delta yi over delta t, we get y prime of t. And so we have x prime squared plus y prime squared under a square root. In this way, the formula that we're integrating is very much connected with Pythagorean theorem, and therefore is fairly memorable. If we're trying to get the sum of the little diagonal type pieces, then we expect that those diagonal oriented pieces can be computed with Pythagorean theorem, and that's what we have to sum up or integrate. So let's go ahead and write out another little notation for this. So we can actually represent that horrible looking expression in there, ds, as x prime. We can represent that horrible expression as ds. So I'm going to let ds equal x prime squared plus y prime squared, and then dt. And so this is what we're going to call ds. And part of the reason we give it a name is because we're going to have to do something else with areas of surfaces that make use of this, and so that's going to make it convenient. But the other reason is if the length of the curve is s, then we are integrating ds in order to evaluate that. And so this is introducing you to a notation and an expansion upon our notion of differentials and the relationship with integration. All right, so now that we have a formula and a variety of forms here, let's actually do a concrete example. And I'm going to do a simple example that we can actually do with geometry, because that'll make it easy for us to verify whether we've done it correctly or not. So suppose I've got x equal 3 times cosine t, and y is 3 times the sine of t. So hopefully by now you know and you recognize that this is going to be a parametrization of a circle. And if I'm going to look at t ranging from 0 to 2 pi, I expect that's going to be one lap around the circle, and the length of that curve is going to be the circumference of the circle. So my expectation is that the length is going to be 2 times pi times the radius of the circle, and so 6 pi. But how do we do this with the techniques that were just described? So the first thing I need is x prime of t, and that's -3 sine t. I also need y prime of t, that's 3 cosine t. So I'm going to integrate from 0 to 2 pi my ds expression, which first of all involves a big square root, and underneath that square root you're doing a Pythagorean theorem type computation. It involves x prime squared and y prime squared. So we'll have -3 sine t squared plus 3 cosine t quantity squared dt. Now let's do a little bit of simplification here. So when we square these, we're going to get 9, and then we can actually factor out a 3 from the entire expression. So let's do that. That actually makes it the easiest. So here I have a 3 squared, there I have a 3 squared. I can factor a 3 squared from the entire expression in the root. That becomes a 3 outside of the root. And that leaves me sine squared t plus cosine squared t. Let's make sure my t's do not look like my plus signs. And of course we know that sine squared t plus cosine squared t equals 1. So here we have the square root of 1. And so we're just integrating dt from 0 to 2 pi. So that's an easy integral. We plug in, so we'll have 3t evaluated from 0 to 2 pi. And indeed, that comes out to be 6 pi. And so in this simple example, we see the arc length formula using an integral demonstrated, but we're also able to confirm that it works with our circumference formula. In general, it's good to do a simple example to verify you know what you're doing, and then therefore later on a more complicated example where you don't have simple geometry, you're confident in the methodology. So that's all for now. That is arc length. Next, we're going to do a little bit of surface area. But remember for the arc length formula that you are going to integrate between the appropriate t values, x prime squared plus y prime squared under a square root. All right, until next time.